And we'll just start that today, and we'll be finishing it up on tomorrow. Rational functions. What is a rational function? Well, we defined that early in the course. Let's put it up here again. It's just if I take some r of x, r for rational if I wanted to, and that's just one polynomial, p of x, over another polynomial, call it q of x. Or polynomial. So it's a quotient, if you will, of two polynomial functions. That's what a rational function is. Now, what are the things that we're concerned about with rational functions? Well, the first question that comes up is always the domain of that function. Now, it turns out that the domain of r of x is all points, or all values x, such that q of x is not equal to 0. It's going to be very simple. Any value will work other than if I end up with a 0 of the polynomial q. Remember, we did zeros way back then. 0 is a polynomial. That's where it comes into play. So the domain is the set of all elements x. X is a real number, and q of x cannot equal 0. So when we look at real examples, we have to analyze that polynomial function. We find the zeros and we exclude them. Now the range is a bit much more complicated. That's where we're going to look at the graph to give us some idea. We're not going to spend a lot of time on that because in the calculus will develop tools to deal with that. Because we can have some very elaborate looking, functions. They can, look like this. And something that kind of look like, let's kind of like take a look like something like this. It can kind of go like this. It can also go like this. And like this. It can have to do all sorts of things. So here we have to exclude this region here. Here's going to be plus or minus infinity. So finding the range is a lot more complicated with these sort of problems. So we won't address that right away. We'll look at the graphs and be able to do that. Okay, but we do want to address this whole idea of this domain problem. How are we going to do that? Let's take a look at some examples. Let's take a look at a simple example. And along the way, we're going to see some interesting things happen. So let's take my f of x is just equal to 1 over x, the most simple rational function I can create. So if I'm looking at this, the domain of this is a set of all elements x. X can be any real number other than 0. We have to exclude 0. 0 has to be excluded. I set my q, which is x equal to 0. I get rid of 0. Now, if I plug this in to my calculator, I get a graph that looks like this. That's what it looks like. I get a strange behavior around 0. Now, if I looked at, there's my domain. Let's see. Like I said, it's hard to find out the range, but there's a little subtle point here. Let's see if we can figure this out. Let's try the range. From that picture that I just drew, what do you think the range? Okay, those are the y values. Y can be any real number. Are there any values that y can't be? Turns out that you may not recognize it, but there is. Y can get as close as we want to but never equal 0, meaning x would have to be infinity. And we can't get to infinity. We can get closer to infinity. So y equal to 0 is not an output I can get from this function. If I put in an x, I can never get 0 out. I can get damn close to it, but I can't get 0 out. So over here, we can actually figure this one out. That's a little subtle point. So the range is any number other than 0 for y. Okay, so we can have this strange behavior. Now this line that's forming over here, let me put it up here, this sort of a line that forms right here. And that's the line that x is equal to 0. We give that a special name. Lines that cause this behavior, meaning as I go from, get closer and closer to that x equal to 0, I either go to plus infinity or minus infinity or even possibly both. The line x is equal to 0 is called a vertical asymptote. A vertical asymptote. Now let's take a look at another one. And then we're going to define it at the end, and then we'll show you how to find it. Say, for example, I look at another function. Say f of x equal to 1 over x squared. What does the graph of that look like? Well, same sort of thing. Notice I still have that same problem at 0. When I said x squared equal to 0, that still gives me x can't be 0. Well, when now I put this in, my graph looks something like this. It still gives me that same vertical asymptote. It should be closer, but it's not. At x equal to 0. But now notice, as I approach from either side, I'm going for both cases up to plus infinity. Where on this side, I went to positive infinity, coming from the right. Coming from the left, I went to negative infinity. Again, that's another vertical asymptote. Okay, let's change it very slightly over here. So here's my first example. Here's a second example. Let's do a third example. 1 over x minus 2. Okay. Now, when I want to find the domain, it's not just excluding 0. So what do I have to do? I have to set x minus 2 equal to 0. Solve that, and that tells me x is equal to 2, and that is the value that has to be excluded from the domain, because I can't divide by 0. So what does the graph of this now look like? What changed over here? Well, what happens is my value x equal to 2 has to be excluded. And what's happening here? The vertical asymptote will shift down over here. That's x equal to 2. And it's going to be similar to this one, and it's just going to shift everything down 2 units, so it's going to look something like this. Okay, so you might ask the question, is whenever the denominator gives me 0, is that always a vertical asymptote? The answer is no. I'm going to show you why. But this happens to be a vertical asymptote. So you might say, are all excluded values from the domains vertical asymptotes? And we're going to show you that they are not. So that's a question, and it seems, it seems like what's happening over here. If I look at the first few examples, first question a student might come at and ask, they'll say, are all the excluded values from the domain vertical asymptotes? And I'm going to tell you right now it's no, and I'm going to demonstrate how and why. We're going to look at another example over here. So just because the function is undefined does not mean you have hit a vertical asymptote. There's a certain condition that has to be met. So let's consider this example over here. I have this problem right here. That's now a much more elaborate looking rational expression. First thing I want to do is let's address the domain issue. Okay, so I come over here and I set the denominator, that q, equal to 0. Well, here the zeros are easy. I can actually factor this. X plus 4, oh, this, I want that. Oh, no, I want that. X plus 4 and x minus 3. Yep, I did it right in my head. X minus 3. So what values must I exclude from this? Well, x cannot equal, in this case, a -4, and x cannot equal a +3. They have to be excluded. So if I was going to look at the graph of this, I'll show it over here. Your first inclination may be, okay, I have two excluded values. So over here at -4, and you might say, oh, that should be a vertical asymptote. X equal to +3. Okay, if I kind of go the same strategy, maybe that's a vertical asymptote. Let's put it in and see what happens. And then see what's going to happen. Looks like all strange things will happen. But let's plug it into a calculator, and then we're going to analyze this a little bit more and see what indeed we get. And you're going to see something a little bit different is happening here. Unexpected from what we just had been looking at. So let's take a look at that. We have, so I have my x minus 3. Let me do this out. So x minus 3 and divided by x squared plus x minus 12. Let's get rid of this other guy over here. Oh, get rid of him. And let's make this a little more manageable now. In fact, let me change this a little bit. Go from, say, -8 up to 8. And with the y goes, yeah, that's reasonable for y. Okay. Notice here, you know, at 3, there is no vertical asymptote. Here I do have one when x is equal to a -4. That does give me a vertical asymptote. But what happens at 3? Well, if you zoom in and you plug on 3, you're going to see something interesting. Well, this 2.99, let's see if I can get to 3. What does it say for 3? It says it is undefined. So there's actually a hole in the function. So the real graph of this function, as you can see over here, does have a vertical asymptote here. So it looks like this. So over here, it follows that same asymptotic vertical asymptote behavior. Over here, however, it does something different. And what is happening here is you have a little hole, and that's how we're going to represent it. It's a hole. So the answer is no, it's not a vertical asymptote, essentially. It could be, but it could be a hole in the function. We call this sometimes a removable singularity. And why is that? Well, we know algebraically we can do a little work here. So algebraically, I can write this as x minus 3 over x plus 4 times x minus 3. Now, I can now cancel these factors, but if I do that, I'm saying x can't be equal to 3. If x is equal to 3, they're no longer equivalent, meaning I could cancel, and write that as 1 over x plus 4. This function does not equal that function everywhere. At x equal to 3, they are different. This one has a hole in it, this one doesn't. Because if I just looked at 1 over x plus 4, that one is okay at x equal to 3. So they look very similar, but they are not the same thing. So if I put over here, y equals 1 over x plus 4, they look the same, and the purple one over here, when I come on top of the purple one, it's 3x. I get 3, I get a number, 0.0143. But on the other one, when I go to 3 over here, it's undefined. And you put a little, see a little circle with a hole in it? That's what's happening. I wonder if it zoom in, it's still going to do that. Yeah, they don't quite, I thought they might actually put it in to show you that. But you can see on either side of it, it's okay, but at 3, undefined. And there's a hole in that function. Okay, so what is the condition for a vertical asymptote? So let's find the definition. We'll end with that. So you have to do a little testing over here to find those vertical asymptotes. And this is something when you get to the calculus, you will define more rigorously using something called a limit. We're not going to introduce limits. I want to get you prepared for limits without having to introduce them. So when you get to calculus, which is about limits, things are going to be a lot easier to work with. So let's take a look at a very simple definition of a vertical asymptote. And we'll end with this. Okay. So given a rational function, R of x is a p of x over q of x, or f of x over g of x, however you want to write it. And given a number a, and given a number a that is a real number, such that q of a equals 0, meaning I get a 0 in the denominator. So that's the first condition. You have to give me a 0. That has to be true. Then, if as x approaches a, and I'm going to put some words over here, from the right, and I'm going to write this in this way. Instead of a from the right, I could write it x approaches a, and I put a little positive. That means to the right side, from the positive side. So if as x approaches a from the right, which I can write like that, my g, or I'm call it Q over here, Q of x approaches either plus or minus infinity. It could be plus or minus, it doesn't matter. Then x equal to a is a vertical asymptote. Then x equal to a is a vertical asymptote. In a similar fashion, if as x approaches a, and now I'm going to go from the left-hand side. So it's to the left of the value a. And q of x approaches either plus or minus infinity, then x equal to a is also a vertical asymptote. Is a vertical asymptote. It has to go to either plus or minus infinity. In the other case, it didn't. It just went to a fixed value, so it didn't go to plus or minus infinity. So this is our definition, and you can see it graphically because you're getting this, either this behavior, it's going to be either split like this, and there's my vertical asymptote, or it could even be split like this, and here's my vertical asymptote. If it's a little hole in the function, you won't see it. You'll have to test for it. Like I had to go specifically to that value and test for it. But that's our definition of a vertical asymptote. You have to go, say this is my x equal to a, and here I'm approaching a from the right, to the right side on the number line. Here I'm approaching a from the left-hand side. What happens? Here I go to minus infinity. Here I go to plus infinity. In this case, if I approach from the right or the left, both of them are going to positive infinity. They could also flip down here. They could both go to negative infinity. But that's how we define a vertical asymptote. How you can use your calculators to find those kind of excluded values, those holes in the function. So let me kind of quickly go online and show you that, and then we'll go for some of the other questions, so I don't forget about that. Our calculator, and I put in the function that we had yesterday. And we take a look at the graph of that function. Now, again, we know when we factor the denominator, there's two problems. When x is equal to 3, x is equal to 4, and x is equal to, or negative 4 and x is equal to 3 when you factor that. And over here, you don't see a problem when x is equal to 3. So how can we determine that there is an issue? There's a couple of different things you can do for this. You can use your calculator mode and do a value calculation. Okay, hit value, and I'm going to plug in x equal to 3, and it will tell me nothing for y. It gives me no output for y. So there's no output for y. That means it doesn't exist there. So that's not a possibility. Another option over here is you can actually go and look at your table and do a table set. And you can start the table, say, in this case, I'll start it at 0, and I'll go in increments of 1. I go down here in increments of 1, delta table, that's 1. And then if I look at my table, it's going to start at x is 0 and increment it going in increments of 1, and it's showing what you have. And at x equal to 3, you get the error message. That's not as easy and as elegant as Desmos, but there are ways around it using this calculator. So I just figured I wanted to show that to you. So two different ways of looking at it as to how to find out when the domain the value that's not in the domain is not a vertical asymptote. So not all zeros in the denominator lead to vertical asymptotes. So you have to check out, and it has to follow that definition that it either has to go to plus or minus infinity as your value of x gets closer to that excluded value. If it doesn't, then it's an excluded point on the graph, which is a little hole in the graph. Okay, so that's kind of brings us up to there. Any questions on the other homework problems that we looked at? Anything there? And we're just looking at the asymptotes in the 11.4 and 11.2. We just looked at the general end behavior of square roots and cube roots and stuff of that nature, and finding the domain of square roots functions. So any questions there? Are we okay? Yes, Ashley.
I just have a general question. So when we factor the denominator and we're looking to see what will make it undefined, it's either going to be a vertical asymptote or it's going to be a hole in the line, right? It's always going to be one or the other? Okay.
One or the other.
And that's why we factor it, because we are looking like on a calculator, it's not so easy to see as in Desmo. So is that why, like, if it's going to be like undefined at +3 in the calculator, we're going to set it like you showed us right now, and that's why like we search for it?
You can, if you find those zeros, you're going to test all those points that you're excluding from your domain.
Okay.
And if when you grab it, you don't see a line going up and you want to double check yourself, you check that point that you don't see any strange behavior on your calculator, such as 3 in that case, and then you see at that point exactly x equal to 3. In one case it said error, and the other case it just gave me a blank for y, meaning there is no y that I can associate with that value.
Okay,
So
I'm just making sure I get it.
So that's the first step, though, is you want to find the domain, get rid of all those values, and then ascertain, is it a vertical asymptote, or is it just an excluded point, meaning a little hole in the function? Well, that's all you do. That's all you do for the rational functions. Now, when you get to the calculus, you're going to introduce a new tool and a new technique to do this more rigorously and with more precision. We're kind of doing a little bit of hand waving here, but we're getting you ready so once you get to that point, it will not be a giant leap to go from this idea to the concept of the limit. And that's the focus of calculus. It's all about this idea of limits and understanding them. But here we're kind of bringing you right up to the edge without pushing us over. And it will get you more ready for that. So any other question? Anything else? Before we close out the rational functions today, and then we'll, starting next week, we'll do a quick thing on going back to our trig functions and then back to our logs and exponential functions, and then looking at all those functions in general, because that's what calculus does. It analyzes all these functions, and we're doing it with pre-calculus techniques. There we're going to introduce calculus techniques and then enable us to analyze them more thoroughly and more efficiently. But, so no other questions? Anything else? Homework's okay. Hopefully everyone's doing well. Closing out of another week. So we're going to 11.4 continued. It's all about our rational functions. And so far we've looked at the domain of these functions, and that led to looking at vertical asymptotes. And the definition for that. Okay, there's two more things that we want to consider today. We want to look at what happens as the end behavior, and that's going to lead, or it can lead, doesn't always lead, but it can lead to something we call horizontal asymptotes. And then we're going to have another look at the range again, but we're going to do this approximately using the graph. So those are two more things that we would wish to cover today. So let's start by looking at that end behavior of our rational functions. Let's start with a simple rational function. That's the same one we looked at earlier. So we'll start with our f of x equal to 1 over x. Now the end behavior, that looks at what happens as x goes to either plus or minus infinity. Well, let's just throw the graph up here so we can get a picture of what we're dealing with. You can use your calculator. I'm just going to use my head calculator and draw the graph of that, approximation to it. We already know this has a vertical asymptote at 0. Well, this graph looks something like this. So I already discovered that there is a vertical asymptote right here where x equal to 0. Because if x gets closer and closer to 0 from the right, I go to plus infinity. As x gets closer and closer to 0 from the left, I go down to minus infinity. So that's what's happening around the excluded value from the domain, because the domain of this is all real numbers other than x equal to 0. The question we now have is, what is the end behavior? What happens as n gets very large? Well, you can see what's happening over here. It seems to be getting closer and closer to the x-axis, which is y is equal to 0. And that kind of makes sense. If a larger and larger number for x, I put in 10, well, my answer is 1/10, or 0.1. Put in 100 for x, 0.01, 1,000, 0.001, 10,000, 0.00001. It keeps getting smaller and smaller. Same thing happens here. Now, if I put in negative 10, I get negative 0.1, negative 100, I get negative 0.01, but it gets smaller and smaller and goes to 0. So from here, as x goes to either plus or minus infinity, what happens, my f of x gets closer and closer to 0. And that's the y value. We call that, when that happens, we call that a horizontal asymptote. And you kind of can draw the picture of it right here. So you can draw a horizontal line, and that's y is equal to 0, and that's what we call a horizontal asymptote. We approach a fixed constant value. Okay. Now, this one, it just turns out that the y and the x-axis happen to be the vertical and horizontal asymptotes respectively. That doesn't always happen. Now let's kind of look at some other types of functions. Then I'll define the horizontal asymptote more specifically. But essentially, it's, I kind of gave you that definition. But that's what we mean by end behavior. What happens at the very extremes of our functions. So let's take a look at say another example over here. And let's say we had the following. F of x is equal to a x plus 0.3 over, or 2x plus 3 over x minus 1. And let's kind of take a look at this rational expression. Let's first start by analyzing and finding its domain. It's a relatively easy value. So hopefully everyone can see the domain is relatively easy because I only have the binomial x minus 1 in the denominator. So the domain has me looking at x minus 1 equal to 0, so I get x is equal to 1, so I exclude that. So my domain, set of all elements x, such that x obviously is a real number, but it cannot be equal to 1. You could even look further into that, and you will see that that is not an excluded value. When you graph it, you're going to see at x is equal to 1, you're going to see something like this. So if I plug it into my calculator, and my graph looks at x is equal to 1 over here. I put it in as a line over here. You can see something like this starting to happen. And down here, something like this. X equals to 0. X equals has, okay, 1.5 about here. So I'm drawing it by eye over here. But that's what it's going to look like, something like that. In fact, let's just kind of show it. I'm doing it by my eye. Let's show it more precisely. You have these, technology resources at your disposal. Use them. Calculus and pre-calculus can, due to what Rene Descartes did, have become very visual, very geometric. They can use that as a tool to analyze things much more effectively. Not only do you have the algebraic tools, but you also have geometric tools where you can kind of see the picture. So y is equal to 2x plus 3 divided by x minus 1. And let's kind of zoom out over here so we can kind of see everything, except for what I had yesterday. So I go from, say, minus 5 to 5, and it's minus, I don't know, I'm just picking it up, 8 to 8 something, just so we can kind of see a little bit what's happening over here. So similar to what I have drawn over there, and let's put the line x equal to 1 there so we can kind of see our, if you will, our vertical asymptote. Okay, so that's our picture. Let's zoom out a little bit, kind of see what's happening over here. Okay, so there's our picture. You have that using Desmos. You can do the same thing on your TI calculator, just so much quicker and easy for Desmos. Now, we've already done that. Now we're asking about is the end behavior. So now we kind of change our focus a little bit and look at the end behavior. So what happens as x goes to either plus or minus infinity? Well, let's look at it this way. Let's get x to be larger and larger values. So what we could do, if we wanted to take the time, we could set up a little table of values. This is a long way. You don't have to do that every time. But there's my x, and there's my y. And I could put different values in for x. Say, for example, I put in x is equal to, say, well, let's start. Let's go a reasonably large value, 10 for x. So what does that give me? 23 over 9. Plug that into my calculator. 23 divided by 9. And I get roughly 2.6, approximately 2.6. Okay, let's put in, now I'm going this way, positive x, put in 100, so I get 203 minus, or over 99. And I get 2.05, approximately, 2.05. Let's put it in 1,000. So I'm going way out along the x-axis. So I get 2,003 over 999. And you might start to see a pattern over here. I get 2.005. The larger x gets, the closer this gets to being 2. So if x goes to infinity, it looks like, the pattern looks like this is getting closer and closer to 2. Not 0, not 1, 2. A y value of 2. If I go 10,000, this would be 2.0005, and I keep adding another factor of 10, I add another 0 in front of the 5 over here, and it'll get closer and closer. So that seems to be suggesting that y equal to 2 is a horizontal asymptote. And that's one of our conditions. So this is the y value, so y equal to 2 is what we call a horizontal asymptote. Now, a horizontal asymptote does not have to be the same in going to plus infinity or minus infinity. This one happens to be so. Now, let's flip it around and do the other approach by now allowing x to go to negative infinity. So set up a little table over here, x, y, and let's put in negative 10 for x. And I get negative 17 over negative 11, so negative 17 over negative 11, and that's, you know, a positive 1.5 approximately 1.5. Now put in negative 100. I get a negative 197 over negative 101, which is approximately equal to 1.95. Let's go to 1,000. Negative 9,997 over minus 1,000 and 1,000, excuse me, 997 over 1,001. So 1,997 divided by 1,001, and I get 1.995. And you'll start to see the same pattern here. As x goes to negative infinity, this gets closer and closer to a positive 2. Again, we can say there's my horizontal asymptote, y is equal to 2. Now this particular one, if I go over here and plug in y is equal to 2, there it is, that's my horizontal asymptote. And let's see if that's the case too. We can validate that graphically using a tool such as Desmos. I'll just put that value that I just found in, and then we're going to see the shortcut for being able to find it. There's always shortcuts, but first we wanted to kind of give you the picture. Okay, so now let's put the other value in over here, y equal to 2. And you can see as I zoom out here, that blue line is getting closer on both sides to the black graph of our function. Y is 2x plus 3 over x minus 1. So as I go out to either plus infinity to the right or minus infinity to the left, I get to the same constant value. Now, it's not always going to be the case that when you go out to the plus infinity on the right and minus infinity on the left, that you will always get the same value. It can be different, just to let you know. More often than not, however, it's not. It's more the same. But notice it's not just 0. Everything kind of shifted up. And that's what the case. Now, here's another way of looking at this. And this can be very helpful. And if I look at my function over here, you might see a pattern from what we just did there. Say x is large. If x is large, and it doesn't matter if positive or negative, I'll just take it being positive, large positive value. Well, what about 2x plus 3? Well, if x is 1,000,000. Well, this is 2,000,000 plus 3. Well, if x is large, you can pretty much ignore that number. 2,000,000 or 2,000,003, not a hell of a lot of difference. So you can ignore that. Same thing over here. If I have x minus 1. Well, if x is 1,000,000, so minus, 999,999 versus 1,000,000, or minus 1, that doesn't really matter. So we can ignore that. So this expression, f of x, when x is large, looks a lot like 2x over x. Canceling the x's, I get 2. That's my y value. There it is. There's my horizontal asymptote. And yes, you can do that at work. But a lot of times you want to justify this. And we're going to see later on how you do, and you will see later on in the calculus how you go that a step further. Okay, so that is my horizontal asymptote. Table forms, you can also argue this way. I mean, here's another way of looking at it. this is what we sometimes do it algebraically, and you'll see this trick in the calculus. I'm going to take and multiply top and bottom by 1 over x. Now this is not valid when x is 0, so it only applies when I'm way far away from the origin. If I distribute that, this is the same analysis here, but done in a different way. And that gives me 2x over x plus 3 over x in the numerator. And then in the denominator, I have x over x and, minus 1 over x. Well, I can simplify this a little bit by canceling the x's. So that's 2 plus 3 over x. This is equal to 1 minus 1 over x. Again, let x get really large. Well, what happens to 3 divided by x as x gets large? Well, as x goes to infinity, this goes to 0, because I have 3 over a larger and larger number, this goes to 0. What happens to that as x goes to infinity? Yeah, the same way this goes to 0, that also goes to 0. So what do I end up with? 2 over 1, there's my horizontal asymptote. That will always work. Not just for this, it's always going to work. Now, sometimes you will have different things, plus and minus infinity. This one happens to work out that it's not the case. But that is essentially the end behavior we're looking at. We're not caring about what's happening here. We're already taking care of that by looking for my excluded values and finding a vertical asymptote here. We're now looking to see does it have a horizontal asymptote. Okay, so let's write the semi-formal definition for a horizontal asymptote now. And let's kind of put that up there, and we'll kind of use that as our guideline. Let me clear this out, and I'll put up the formal definition. Here we just kind of introduce it graphically and also algebraically, table forms. You're going to find there's many ways of looking at it. And it's good because some students see one way and not another, and vice versa. So you always have something to back you up. If you're not sure, you have another way of testing it. You can kind of go through all the different kind of approaches that we've shown here to identify these horizontal asymptotes. So let's write it more formally. So here. So given a function of x, and I've been using p and q. I use f and g in the book. It doesn't matter. Let's just do f of x and g of x. It's just going to be anything like that. F of x and g of x. Now we're going to be able to define this not just for rational functions. This is also going to be able to define for other types of functions as well. So I might include that now. I can do this more generally because it'll actually even apply to our exponential functions that we'll be looking at momentarily. So this in general, it could be some, function f of x. It doesn't just have to be a rational function. It could apply to any function, this definition. And given a function, and as x goes to either plus or minus infinity, and either r of x or, as we have it here, this other f of x, as they go to a constant a, some constant a, then we say that y, because y is my f of x or my r of x, y equal to a is a horizontal asymptote. That's all it is. It's a horizontal asymptote. Very simple. And we're doing this, we're letting x get very large. Now you can either look at it, as a table. So this is one way I'll put it that way. So we can either look at this as a table form, the table of values like I did. One, you can look at its graph and surmise from the graph what's happening. We can look at those two algebraic approaches I had. So for example, if I have, the algebraic approaches, and they both involve the coefficients of the x terms. Now, here you have to be a little cautious. Let me show an example where you don't get what you think you might get. So for example, let's turn around and now look at another rational function, and you have to be careful when you use this 3. That's why the tables and the graphs are always a good first step. So let's take a look at some different types of rational functions, and then we're going to see next week when we look at exponential functions, they too have a horizontal asymptote, but it only goes in one direction, as x goes to either plus or minus infinity. It doesn't do the same on both sides. So let's take a look at another, if you will. I'm going to make this one up, just so you can kind of see. I have x squared minus 1 over, let's take this as 2x plus 3. Now, what I'm going to tell you, what we did earlier does not apply with the algebraic approach. It has to go with both of the x terms. So that's an example of a rational function. But notice the degree of the numerator is larger than the degree of the denominator. This is going to give us something that's going to look a little bit different. Let's take a look at it using our decimals. So you can get such a variety here. That's why you have to be careful about jumping on board with any one approach. That's why you need to be able to look at it in several distinct ways. So let's try this one. Y is equal to x squared minus 1. Oops. Divided by 2x plus 3. And notice what happens here. It gets all this crazy stuff happens when x is equal to negative 3/2. I zoom in here, right here. Let's put that in. X equal to negative 3/2, 1.5. I do see there is my vertical asymptote. But what happens? As x goes to either plus or minus infinity, as I zoom out, there is no horizontal asymptote. Now, in some books, they'll talk about something called an oblique asymptote. You may discover that if you go on. I chose not to add it here. The horizontal asymptotes are the more important ones, but there's something called an oblique asymptote that this has that you don't need to worry about. We can find that simply by doing long division, but there's enough in this course to begin with. Most of the time in calculus, you might see it mentioned and maybe not. It's like, 6 to 1, half a dozen of the other. Some people might mention it, some people might not. Reason being, it's the horizontal asymptotes are much more critical. They talk about stable behavior. These other ones don't. So it's not as universally discussed. But what you don't see is approaching any fixed line y equal to some constant 2, for example. See, I don't have anything there. Let's take a different color of that. Make that different color. Make it red. The lines don't approach any constant value, no matter what I change my, y to be. It's not getting closer to anything at all. So in this case, this one has no, if you will, no horizontal asymptote for this one. It has a vertical asymptote, but no horizontal asymptote. You plug in your tables of values. This is going to go when x goes large. It's going to go large positive values. This is going to go to plus infinity. When x goes large negative values, well, this is going to be positive. That term's going to be negative, so that will go to negative infinity. So there is no fixed value that I approach. So sometimes I have them, sometimes they don't. This doesn't happen to have any. Okay. And I always saw it with a picture of it at first. I mean, I look at it and I could see right in my mind, I say, okay, higher degree than this, horizontal asymptotes are not going to occur. Anytime the numerator is a higher degree than the denominator, you will not have a horizontal asymptote. You need the degree of the denominator to be larger than the degree of the numerator for it to happen. So that's an example. Let's take a look at another example over here. Here's another example. So we have x squared plus 3 all over, and I'll factor this already for us. X plus 2 and x minus 1. What I'd like you to do is try to analyze that a little bit. Find its excluded points. Find out, are they indeed vertical asymptotes or not? And then see and test for any possible horizontal asymptotes. So try that on your own. You can either use Desmos, use your calculators. Take a look at that. I'll give you a couple of minutes to analyze that. The first thing is the domain. Yes, Ashley.
Sorry. You said if the numerator is larger, there's no vertical asymptote or there's no horizontal?
No
Sorry, I missed that.
horizontal.
No horizontal?
There's no horizontal.
Okay, so the numerator
Anytime
first.
this is larger degree, you will not have a. If it's the same, you will, or if it's less, you will always have it. I'll put this exactly what it is in a second. I'll summarize that.
Does the does anything tell you about the, sorry, I can't get my thought together, the vertical asymptote? Like if I look at something, will it give me an idea of a vertical asymptote?
The only thing that's going to tell you is the denominator when it's 0. That gives you possibilities.
Okay.
Both of those are possibilities. X equal to 1, x equal to negative 2. So you just ignore what's happening in the numerator and just focus for the vertical asymptotes. All the action takes place in the denominator.
Okay, perfect. Thank you.
So only the excluded values of the domain have the potential to be a vertical asymptote. In this case, both of them are. Because you don't have a factor canceling, no. So the domain is relatively easy. And then you're going to see the following, and we'll show it. Two vertical asymptotes. And then what you're going to see is y equal to 1 is going to be a horizontal asymptote. Now, hopefully everyone's getting some picture like this. And it's a lot easier to use Desmos and your calculators to analyze this because you can actually put in these asymptotes very easily. Where on your calculators, you can't draw x equal to a constant. It doesn't allow you to do that. You can put y and get the horizontal out, but you can't. Okay, the real question some of you may be having here is, okay, how did I get my y equal to 1? Well, the approach you want to do for that, you can either put in table of values, but that's the long way. What I would do over here for this one is I'd multiply the denominator out. So I'd rewrite my function. I have an x squared plus 3. When I distribute those, x squared plus x minus 2. When you compare things algebraically, you have to compare both the same powers together. So over here, I have to compare the x squared and the x squared and both of their coefficients. Meaning, as x gets very large, that 3 becomes insignificant. As x gets very large in the denominator, well, obviously the minus 2 doesn't matter, but also the x doesn't matter. For example, if x is a billion squared plus a billion, well, this a billion squared is a billion times larger than this. So you can ignore both of these. So when x goes to either, in this case, plus or minus infinity, my f of x looks a lot like x squared over x squared, which simplifies to 1. And that's how I get my horizontal asymptote of y equal to 1. So I do that by multiplying out. Yes, you have to compare the same, degrees, the same degree. If the degree of this is larger, there is no. If it's the same, it's the ratio of those leading terms, if you will. There's a slight caveat to that we're going to talk about in a second here shortly. Let's see where the cap went to. Okay. Okay. While we're at it now, we'll come back to the domain. We're just about for the day. And I want to mention one other aspect of this. Let's plug this into our calculators here and see what's happening. So let's go back to Desmos. We'll end with this for today, and then I'll have you take a look at them over the weekend and see how well these things work out and how much meaning you can attach to them. So let's put this other one. Let's get clear. X squared plus 3. Okay, so here we have that little graph that we were just looking at a moment ago. And then you can see I could plug in my various values, values x equal to 1, x equal to -2, and y equal to 1. I have all of these. Let's make this a different color over here.
Professor, I don't know if we're supposed to see the calculator, but I'm not seeing anything on my screen.
Okay, maybe it's today. Oh, I didn't have to hit the last little. There's several buttons. Forgot to hit the last little button over here. That's all. There's so many buttons you have to hit to make these things work out. Let's get them different colors over here. Make that orange, I guess. And let's make a function here. Let's make that black so we can kind of see that. Okay. So I have some vertical asymptotes. You can see my horizontal asymptote there. But now what's going to concern me a little bit more over here is the domain of this function. So if we're looking over here, and let's consider the domain of that function. Look at the graph. Now I notice over here that I can get close to, this will actually hit the value of 1. So a function can always cross its horizontal asymptote. It's possible to cross its horizontal asymptote. It cannot cross its vertical asymptote. Here is where it's crossing a horizontal asymptote. And that's what's nice about, if you look at Desmos, when you click on the function, it shows you, it gives you a little gray circle there that's shaded in that says that's where I intersect this other graph on that line. So that's what's nice. It looks like it, and over here, 10.9, it looks like it comes back up again or something like that. So this is a low point. This is where it intersects. This is a low point of the curve. So over here, that's why it's very hard. This is a hard thing to do when we look at the range over here. This is the low point over here, point approximately to the nearest thousandths, 0.954 we can show there. If we zoom out further, this one over here just approaches it from above. So this is a little bit different than the other one. It never quite gives me that little dot. Okay, that's the smallest value it gets. Now I'd like to know, close to here, what's the highest this middle point gets. So this is where I intersect the y-axis. That's my y-intercept, but it continues to go up. That's what I like about Desmos. It automatically picks the max. So the maximum y value in this range over here is negative 1.398. Now the other one, it was slightly different there. It's 0.954. So what does that mean in terms of our range? What are the allowable values? So if I'm looking at this, this is the lowest value. This one kind of goes beneath it and then comes back up again and gets closer and closer to it. That value here is a height of 0.954. There's a point over here where this is minus 1.49, whatever it was. Let me just take a quick look so I can see. 1.398. Notice in this region here, all this region here, this is a dead zone. All throughout here, I will not get an output. So that's why the ranges for these functions are really, really subtle and difficult. So if I want to look at the range of this function, I could do it approximately. So it's a set of all values y. Y obviously is a real number. And y has to be approximately between these things. Either y is greater than 0.954. So y is greater than or approximately equal to 0.954, or y is less than or approximately equal to negative 1.398. It's an approximation that we get with. I will never get a value, no matter what I plug in here, I will never get f of x equal to 0. I'll never get f of x equal to negative 1. That will never happen. I'll never get f of x equal to 0.5. Those will never happen. No matter what x value I choose, this whole region is excluded. And it's not just the one. It actually dips beneath, as I showed over here, it actually dips beneath that y is equal to 1 and comes down to a low point of 0.954. It's a very subtle thing. These things you find better with the calculus. That's what we kind of reserve that for, is doing the calculus. Okay, so that's what you need to do when you're looking at the domain. Look at the picture. find the low and the high if it's broken up like that, and break it down into pieces. What is my range? What are my excluded values? So you can see I'm never going to have anything, of 0. I'm never going to be -1 or even 0.5. It can be 1. There's a point right here. There's an x coordinate where it is 1. When you plug in x, in fact, you can look at that. We're just about pretty much done here. So if I look at that value, when x is 5, plug in 5 for everything, I will get 1 out for y. Okay, so that's all we have for today.